questions. Yeah.
Yes. Thanks.
Right. Thank you. Thanks everyone for coming here. So today we have James. He did his master's and PhD with the CDT at Cambridge, and he is now a research associate at the Turing Institute. And his works span from probability to now differential privacy and multi-party computation. And today he's going to talk about the secure single server aggregation with polylogarithmic overhead. So Mike, to you, James.
Okay, thank you. Yep, this is joint work with 4 people at Google. Adria was at the Turing when we started, but was at Google by the time we finished. So I'm the only non-Googler left. This is a work on multi-party computation rather than differential privacy. It's linked to some of the differential privacy work that I've been doing because a lot of differentially private protocols require or there's a lot of interest at the moment in trying to do differential privacy on top of secure summation or on top of secure shuffling, commonly called the shuffle model. There have been a lot of papers on that. And in order to do that, we need good implementations of aggregation and of shuffling. But this single server aggregation is also useful for machine learning and in a lot of other places, federated learning type applications. So this is a paper in its own right as aggregation. Okay, so I'll start by laying out the setting and the problem statement. So firstly, what do we mean by secure single server aggregation? Well, by single server, we mean there's going to be one server. There are going to be n clients. So you should think of n mobile phones, each one holding some vector. And the server wants to know the sum of these vectors. And we also want this protocol to be practical, which means that it's going to have to be able to handle dropouts. So we have to allow for some delta fraction of the clients to drop out. So up to delta n clients might drop out during the computation. And the server should obtain the sum of the remaining clients. Obviously, it can't get a sum including data from a client who immediately drops out, but it should get the sum of everyone else's data. And for security, our adversary model, or threat model, if you will, is that the server might be semi-honest or malicious, but in either case, we're going to assume that some gamma fraction of the clients have also been corrupted. And for both the semi-honest and the malicious case, we allow these clients to act maliciously, which is probably important in practice because whilst you might trust a server to act semi-honestly, you probably wouldn't trust every client that might be involved to act semi-honestly. And these clients are allowed to collude with the server. So even in the semi-honest case, you should think of this as a server that is following the protocol exactly, and an adversary who controls some fraction of the clients and can also see the view of the server. The paper that we produced is following on from a previous paper, this practical secure aggregation for privacy preserving machine learning from 2017. This paper doesn't really have anything to do with machine learning. I think they just put machine learning in there because it makes people read papers and pay attention to them. Really, it's just practical secure aggregation. You could call theirs practical secure aggregation with order n overhead, whereas there's a linear overhead as opposed to the polylogarithmic overhead of our algorithm, which is based on theirs. A lot of the components will be the same, so I'll take you through basically their entire algorithm, but we have this way of reducing the cost of running it. Okay, so here's our setting. As I've said, these clients can only communicate with a server. We've got this star topology for communication, but we want them to be able to communicate with each other, and this is easily achieved by having the server act as a relay between the two clients, so long as they have a public key infrastructure in place, as long as they know a public key from each other. And the way we kind of formalize this is just saying in the first step of the protocol, they're all going to send in a public key, and the server is going to send that public key out to all of the phones. So all of the clients will receive everyone else's public key. If you're in the semi-honest setting, this is fine, and they now have secure channels. If you're in the malicious setting, then obviously the server could do a man-in-the-middle attack. And this is somewhat unavoidable. Indeed, the server can actually do a civil attack. If you're taking part in this interaction, the server could just simulate n-1 other clients, all of whom are corrupt, and just steal your data. Add your data together with a bunch of zeros, a zero from every one of these clients, and thus get your vector. And this is somewhat unavoidable. If you don't have a root of trust, you're not going to be able to avoid that. So both in the semi-honest setting and the malicious setting, we in the semi-honest setting, we just trust the server to select n clients reasonably and handle public keys in the way it should. In the malicious setting, or what we call the semi-malicious setting, we're assuming that from somewhere you are going to get a public key infrastructure and confidence that these n parties have been selected in a fair way. We leave that beyond the scope of what we're doing. Okay, this shouldn't say ring topology. That's a typo. But the point is everyone can now communicate with everyone else. We now have these secure channels. There's a problem, which is that this complete communication graph requires big O(n) communication per client. So if you're communicating with all of the clients, then you have to do order n communication. And this is what we're trying to avoid. But I will first explain the method of Bonovets et al., in which all the clients interact with each other. And our innovation will mainly just be that each client only interacts with some subset of the other clients. Of size polylog n, and so the total communication will be polylog n rather than n. At least its dependency on the number of clients will be. So what are our contributions? Well, we have a semi-honest protocol and a semi-malicious protocol. That is a protocol in which we assume the server is semi-honest until it's distributed the public keys and is then malicious. We also describe how to generate a shuffling protocol from secure aggregation. And we provide numerical bounds and experimental results assessing these things. I won't be presenting many of the numerical bounds today, but they're in the paper. Okay. So here's a table of the communication and computation required for each of these two papers. You'll note that at least if you assume that L is order log n, so some of these, or at least order log n, so that the log squared n factors appear, the difference between the costs in the Bonovets paper and the Bell paper, our paper, is that it's a factor of n over log n. So for each client, rather than communicating with n other people, they only communicate with log n other people. Client communication has a plus L on the end and server communication a plus NL. This is because in order to put your vector in, I haven't said what L is. L is the length of your input. So obviously the amount of communication is going to have to be at least the length of your input, whatever it is. And whilst in communication, if L is bigger than N, then the difference might not look that substantial for the client. For the computation, which can be the limiting factor in practice, this Bonovets et al. Stuff is in production, and they're worried about how far they can go. The limiting factor is the computation, which I'll explain where that comes from in a minute. And we improve that by a factor of n over log n. And that's what makes it practical. And we get within a log n factor of the insecure solution. Oh, that was semi-honest. In the malicious case, you get these extra log n factors, but it's still for large L, sorry, it's still within a log n factor of the insecure solution. So what are these numbers in practice? These, more concretely, if we have 1 million clients and 5% of them are malicious and 30% of them drop out, then it will suffice in our semi-honest protocol for each client to have only about 100 neighbors. Whereas Bonovets et al. Were having each client communicate with everyone else. So that would be 1 million in that case. And actually, people only need, for these kinds of parameters, about 1,000 neighbors once we get n up to about 1 billion. And Bonovitz et al. Found that they were practical up to about 1,000 clients. For 1,000 clients, this was maybe a reasonable cost. So for that same cost per client, we can go up to 1 billion, which is probably enough for pretty much any entity that exists in the world today. In the malicious case, things are not quite as good, but still fairly good. If you've got merely n equals 10,000, then it suffices to contact 600 neighbors. It's not so much of an improvement, certainly not as good as the semi-honest case, but it's still a substantial improvement on having to contact all 10,000 neighbors. I should say, in the malicious protocol, there's a slight complication in terms of the security guarantee, because the malicious server can drop clients that it doesn't want if it doesn't want their value included in the sum. So we can't actually guarantee that all honest clients will be included, because some of them can be intentionally dropped by the server. So the guarantee that you get is actually just that there's some constant fraction that will be included, which for n equals, or for these parameters, comes out at about 4,500. And in practice, the secure shuffling requires shuffling a vector of length, or sorry, adding a vector of length 1.3 times the number of clients. So it's linear in the number of clients. I'll get more onto shuffling later. Okay, so how do these protocols work? Well, the basic idea of the Bonovitz protocol, I mean, this is an insecure idea, but the very basic idea is that each pair of clients, or each client has a public key, has a secret key, and the public key of all the other clients. So using this, they can generate some shared secret using Diffie-Hellman key exchange or whatever. So they generate some shared secret that they have with each of the other parties. And they can use this shared secret as a seed to a pseudo-random number generator. And then in each pair, one of them will add that, the result of expanding that seed into a mask. They will add that to their vector, and the other person will subtract it from their vector. And now, once you've applied all of the masks, you send your value into the middle, and they will get added up, and these masks will cancel. Right, that's the idea. This is great. It works. It's secure. There's just one slight problem, which is that I said we wanted to resist dropouts, or we want to be robust to dropouts. So what happens here if a client drops out? Well, what happens is that the mask that they, one of the masks that they had added or subtracted to their number has a partner somewhere at some other client that's been added or subtracted to that value, and you've got nothing to cancel that with now. And so because you don't get the information in from one of the clients, you can't get any information from everyone else's values. It's like they've been masked with uniform randomness. Okay, so we need to get around this problem. How can we do this? Well, note that if the server at this point, if someone had dropped out and hadn't sent in their YI, so if client I hadn't sent in YI, then if the server could just learn client I's secret key, then it would be able to compute all of the masks that should have been applied and work out that part without the XI included, and thus effectively remove these masks from everything else and still get the sum out with just that one client removed. Now, obviously, it seems like a bad idea for the server to know each client's secret key, so we only want them to learn the secret key in the event that that client drops out. So how are we going to achieve that? Well, the idea from Bonovitz et al., and I think this is kind of, I mean, everything that appears on this slide is kind of pretty straightforward. It wouldn't be interesting enough to make a paper probably, but so the main idea from Bonovitz et al. is probably this, which is to use some Shamir secret sharing. So the idea of Shamir secret sharing is that given a secret key, you can cut it into multiple pieces. So 4 here is n-1. So each client cuts their secret key into n-1 pieces, such that any t of them can be used to reconstruct the secret key, where t is less than n-1. This is a standard primitive that I'm sure most of you are familiar with. Okay, so client I sends out all of these shares, 1 to each of the clients that it's communicating with. And then if client I drops out and maybe one of the other clients drop out, then the remaining clients still have enough shares, or the server can tell all the clients, hey, client I dropped out. I need you to send me, I need to reconstruct the secret key of client I in order to be able to remove the masks. And these phones can then send in their shares, and the server can reconstruct that secret key and thus remove the masks that client I, or that had been applied by people using a shared secret with client I. Okay, and this should be correct so long as not too many people drop out. So as long as the threshold is lower than the minimum number of people who will still remain in after we've had the dropouts, and it should be secure so long as the malicious parties can't do this reconstruction of their own. Note this is assuming a semi-honest server. If the semi-honest, if a lying server could just say this person has dropped out, and when they haven't, and thus get their secret key and thus read their value in the clear. So that's something we need to worry about for the malicious case. But in fact, we don't just need to worry about it for the malicious case, because there might be a delay. So if client I is delayed, then the server might honestly assume, or semi-honestly assume, that client I has dropped out. And so says, right, I need everyone to send me the shares of client I's secret key. And suppose they do that, and the server then computes the secret key of this party, and then this party comes back online, or maybe their message was delayed in the network for a while, and it arrives and the server sees YI. Well, at this point, there's a problem, because even a semi-honest server can use YI together with the shares that it reasonably acquired to reconstruct XI. So we need to find a way around this. Bonowitz et al. Needed to find a way around this, and they did. And the solution is to have another mask, BI. So this is, for each client I, just generates one mask from a seed and adds that to their YI. So this is now going to be included in the sum that gives YI. And also secret shares that amongst all of their neighbors. So now if a client drops out, then the server will ask to remove their the masks that they have shared with other people, the key to do that. And if they don't drop out, then the server will only ask for the key to remove this second mask, this BI. And the key point is that the server should only ever receive one of these secrets. So if YI is going to be included in the sum, then the server will be shown BI. And if YI isn't to be included in the sum, then it will be shown the SIJ. Okay. And because we know that the server should only ever be reconstructing one of these, no honest client should ever give up a share for both of these things. And now, even in the malicious case, so long as you bump up the parameters a little, a malicious server can't reconstruct, you bump up the threshold a little, the malicious server can't reconstruct both of these secrets for any one client at once, because the honest clients won't play along with that. And that's the basic idea for why this is secure. Okay. So that's the Bonowitz et al. Protocol. So what did we do that was different? Well, we came along and said, you seem to be relying here on the fact that if you look at all n of the parties, at least a certain fraction of them are going to be honest. and that's true, but maybe you don't need to have these n neighbors. Maybe if you just share your secrets, you'll come up with a shared seed, a shared secret between just you and say k neighbors for some k that's less than n, that will suffice. In that you can be confident that some large fraction of them will be honest. Some large fraction of those k will be honest, and the server still won't be able to learn both of your keys at once, and enough of them will not drop out that the server will be able to learn one of your shares and thus undo the mask that it's supposed to be undoing. And it turns out that this works. If you have just k equals big O log n, then you can ensure that each client won't have too many corrupt neighbors, will have enough surviving neighbors, i.e. non-dropped out neighbors, that the share is able to be reconstructed, and that the graph is connected in the semi-honest case. Or in the malicious case, where dropouts can be done selectively, we can't quite guarantee connectedness, but we can guarantee large connected components, meaning that your value will be summed with at least some large fraction of the other members, even if it's not all of the honest clients. And so, yeah, we've got some parameter sigma and some parameter eta for security and correctness. And really proving this just boils down to the fact that if you're selecting your neighbors at random, or the neighbors who you trust with your shares at random, then the number of them who will be honest is distributed, well, actually hypergeometrically, but you can think of it as binomially, or really just it's basically a normal distribution is the point. So it's concentrated. That's the key thing. It's concentrated around its mean. So you can just be very confident that if you're taking, 100, if 10% of the most 10% of the clients are malicious, if the million clients are malicious, and you select 100 of them, you can be very confident that you won't have more than 50 malicious clients, and so you'll still be secure. Okay, yeah. In the semi-honest case, actually your neighbors can be chosen by the semi-honest server. In the malicious case, things get a bit more tricky. You have to choose who you're going to trust. You can't let the server choose for you. And indeed, just because you trust someone with your shares doesn't mean they trust you with theirs. If you're choosing people uniformly at random, then you need to choose who you are going to trust, not who should be trusting you, because obviously malicious people could all gang up on one person and tell that person to trust them. So just because you're sharing a secret with someone, your secret shares with someone, doesn't mean they'll share the secret shares with you, but it does mean you'll add a mask together. And that's fine, and it all works out. Okay, so the only other thing I have to go over here before we get on to conclusion and open problems is how to do shuffling from this secure aggregation. So what is the shuffling problem, first of all? Well, if each of n parties has a message, so m1 up to mn, we want the server to receive the multi-set of these messages, or a list of these messages that's shuffled. The point is it shouldn't know which message is coming from where. We want to strip off all information about who sent in what message. So you can think of this as maybe returning the messages, but in a sorted list or in any kind of standard representation of a multi-set, or equivalently just if they were completely shuffled beforehand. If the order of them is uniformly random, then there's no information about which one came from who. And there's a simple way to do this, I suppose. You can just set out this vector. So these boxes in the middle of the screen are meant to be a vector. And each person is going to, the basic idea, each person is going to put their message in one entry. So assuming the vector is a single field element, that the message, sorry, is a single field element, and they're going to put that in one position in the vector and set all of the other entries to 0. So each person does that, and then they add up all of these one-hot vectors, and the result is a vector that will have one message, or each of their messages appearing in one place, and the server can then read off these messages. Okay, that's great, except that they might collide. So in order to have no collisions, it's important that we have we need order n squared entries in this vector in order to have order constant probability, or probability a half of there not being any collisions. And furthermore, even if there is a collision, we don't necessarily know. I mean, we will know that there has been one somewhere because there won't be enough messages, but you might be thinking, well, we'll just do something that's order n, we'll drop a tenth of the messages, that'll be okay. So long as we've got 90% of the messages, maybe that'll be enough for us to learn the things we want to learn about the population. And indeed, it might in some circumstances, but with this current protocol, you wouldn't know which of the entries contained a message and which of the entries contained the sum of two messages. And you might mistake the sum of two messages for a message. So we need to do something better than this, but you can do better than this. Right, so what's going on here? So firstly, in order to be able to detect collisions, you can see that the first entry, the M1 and MN are colliding here in one of the places that they're going, in the middle. This place here, if you can see my cursor. So rather than just having a single, rather than just having a message in the thing that they're putting in this entry, they're going to append a counter to it, which has the value 1. And the point is that if two messages collide, then now you can look at the counter and you can see that the counter reads 2 after they've been added together rather than 1. So you'll be able to detect that a collision has happened. Okay, so we now know where the collisions are. That's useful, but it doesn't help us to stop them from happening. We'd still need order n squared in order to get all of the data through. So the idea of these PI, P1, P2, is these are pseudonyms. So you should think of these as maybe uniformly random 128-bit values. So each person generates a uniformly at random a pseudonym which they're going to use for their message. And why is this useful? Well, it means that now we can put messages in more than one place. So you'll note here I've shown arrows for each message being put in 2 different entries. If you did that without the pseudonyms, then when we saw message 2 appearing in 2 different places, we wouldn't know whether that message came from the same person or whether it was the same message being sent in twice. And as I said, we're not trying to find a set, we're trying to find a multi-set. So we care about repetitions. We care about whether this is just the value from the same person appearing twice or whether it's actually a different person, a different source of the message. But by putting in the pseudonym P2, which is from a large enough space that we won't have collisions, we can check the pseudonyms as well, and we can see that these 2 actually match. And therefore we can only count it, and therefore we can get away with only counting it once. We'll know to only count it once. Okay, this is great. So now we can put them in a few different places, and even though here M1 and MN have collided, we'll be able to detect that there was a collision here, ignore what came in here, and just use the value of M1 from the other place M1 was sent to, and the value of MN from the other place MN was sent to. Okay. And it turns out that if you put log n, or order log n, copies of the messages into a vector of length n log n, then you can be reasonably confident that every message will get through. So this collision detection, it now suffices to use a vector of length n log n in order to shuffle these n things. But actually we can do even better. And the way we can do better is by linking up some of the randomness we've got here. So there are 2 pieces of randomness that client 1 needs. First, they come up with some randomness for their pseudonym. And secondly, they come up with some randomness to choose where to put their value, which entries to add their message to. There's no reason why these have to be independent. And indeed, we can make them completely dependent. We can generate the pseudonym to be some random 128-bit value. And then we could have the place where message 1 is placed just be the result of applying hash functions to that value. So we have order log n, or in this picture, 2 different hash functions. So the first position that M1 is sent to is going to be the first hash of P1, and the second place that M1 is sent to is going to be the second hash of P1. Okay, James, you say that means we need less entropy, but who cares? We have pseudo-random number generators. But it's more than that. It means that when you see the value of, you come along to the entry in the vector where M1 is first appears and it hasn't collided with anything, it's got a 1 in it, so you can tell it's not collided. You can then read the pseudonym that whoever sent this message in used. You don't know that it came from user 1, but you know what their pseudonym is. And this pseudonym tells you where else that message was sent. So you can say, okay, I've got this message. Now, I also know that that message was sent to this entry where M1 has collided with MN. So I know that it's been added on there. And I know what it was because I've already recovered it from one place. So now you can subtract the value P1, M1, 1 from this place where they'd collided, and you can recover Pn, Mn, 1 from this place. So even if the Mn had collided in every place it was sent to, it could still be recovered so long as one of the things it collided with was recovered. And you can imagine this as kind of like a peeling process where we go through everything that appears, everything that's managed to go through and not collide somewhere, we can remove from the process. And that will reveal more messages, which we can then remove from the process. And it turns out that with this, it suffices to have only order n entries. If you have about 1.5n or 1.3n even entries in your vector, and you put each value in 3 different places, then with high probability, at least for large n, this peeling process will result in you recovering all the messages. So this gives shuffling from aggregation of linear length vectors. And we couldn't hope for any better than that, because obviously the amount of information that the server receives is just going to be the sum of the vectors, which only contains order n bits of information. If it's, or only contains order L bits of information, where L is the length of the vector. So that can't communicate more than L messages. And it's supposed to be learning these L messages, even if it's not supposed to be learning the metadata. So this is, up to a constant, the best we could hope for. So what have I shown you today? I've shown you 2 secure aggregation protocols, one with malicious and one with semi-honest security. And the point is that they have polylogarithmic overhead, which allows us to handle hundreds of millions of clients. Really, millions is an understatement, for the cost that the previous protocol had per client to handle 1,000 clients. And it's concrete. The system can be implemented in further work, but this should be practical. And I'm pretty sure it's going into production. The secure shuffling protocol that we have, as I've just said, it's optimal in the sense that you couldn't hope to do secure shuffling with a shorter vector aggregation, but you should be able to do shuffling more easily. I feel you should be able to do shuffling without linear overhead in this threat model. So that's another open question or direction for further work, which we're looking into, which is how can we do shuffling in this single server setting with sublinear overhead and a constant number of rounds, really, we would like. If you have loads of rounds, then you can certainly do some kind of mixed net thing, but getting the number of rounds down to constant, especially if you want it to be independent of the security parameter, as well as the number of users, we're not sure how to do. Okay, that's everything.
Right. Thank you, James. as per tradition in this interest group, I'm gonna stop the recording now, so everyone can ask whatever weird questions they're happy to ask.